Down. If Connor's ready, we can go. Are we good?
The clap, right?
Yeah, we need a.
I guess I can clap.
Yeah.
Okay. Great. Dr. Cynthia Reinhart-King. We are so happy today to have our guest, Dr. Cynthia Reinhart-King, with us. There are too many accolades for us to describe in this brief intro, so we'll put them right here. Or we'll try to fit as many as we can. You have currently been the president of the Biomedical Engineering Society. Can you talk about your journey through service in a conference like that? What was that like?
Yeah, absolutely. So I've been part of BMES since I was a graduate student, so 24 years and running, and started by just going to the conference and presenting at it. And then as I started a faculty position, started helping review abstracts, helping chair sessions, then became a track chair, got elected to the board, then became a program chair, and then secretary, and then finally president, and now past president as of a month ago. And
a very brief career.
Well, I mean, I love BMES. I think it's a great society because it's a good integration of undergraduates, graduates, professionals, and faculty. And so, as far as just getting a good exposure to the field, I think it's an amazing venue to do that. I mean, both the meeting, but the society as a whole, I think is just a really fantastic group of people. I think, it's sort of incumbent on all of us to help support the field and the people coming up behind us. And I think BMES is really good at doing that. And so getting involved, like even as graduate students, getting involved in mentoring undergrads who go to the meeting, I think there's a place for all of us to help grow the field, and BMES is a really good mechanism to do that. So when I decided to run for president, it was a real honor to be elected, just because it was a society that I feel really passionately about and a cause that I feel really strongly about. It was a chance to have an impact. And so I'm really grateful for the impact BMES has had on my career, and so it was really nice to be able to give back to it.
And how have you seen BMES grow or change over this time period that you've been?
Oh, it has grown so much. So in the late 90s, it was a small conference that was held at universities, in conference rooms and things like this. And then it was held in hotels, hotel ballrooms and things like this. And now it's 6,000 people held in convention centers, right? So you look at that arc, and it's just grown tremendously. And the number of students attending, students in biomedical engineering in general, has grown significantly. So it's been exciting to see biomedical engineering as a field grow, and I think BMES basically just mirrors that growth.
So when you were starting out as a grad student, was the field of biomedical engineering called that, or was it still kind of being defined in the science world?
Oh, I mean, I think there are some really old departments that have been around for quite some time, but I think certainly when I was first entering, there was still a debate, and I think there probably still is a little bit about bioengineering versus biological engineering versus biomedical engineering, and what those things mean.
Because at Rice, your department is bioengineering.
Bioengineering, right.
Here at Tulane, we're biomedical engineering.
And I think, for the most part, I think we're training the students in the same way, in the same fundamental skills. I think part of the use of the word medical just depends on the applications that you're looking at. And I think there are some people that feel really passionately about those naming schemes. I'm sort of less sort of stuck in that, as much as I think it's really just important for us as a field to define ourselves, because ultimately that's what becomes employable, and making sure industry knows what we are. And I would say 20 years ago that was a problem, really trying to get companies to understand what we're trying to train students to do, and I think much less so now. I think that the field has come a long way in defining what our core curriculum is, what our students are really good at doing, what their utility and their value is once they enter the workforce. So we've come a long way, and I think BMES has played a big role in that, helping to define what the specialty areas in biomedical engineering look like, a strong engineering track, trying to define how to best train students and how to handle accreditation for departments and things like this.
So your research is more biomechanics, right? And mechanobiology. Can you tell us more about that? And yeah, more so in how that field kind of fits into the overall biomedical engineering.
Yeah, absolutely. I mean, I think mechanobiology is a perfect example of something that belongs in biomedical engineering because it requires really good engineering skills, really good knowledge of mechanics. It requires really good understanding of cell and molecular biology to do it well. And then to translate it, it requires good knowledge of things like tissue engineered constructs and animal models and things like this. And so I would say the mechanobiology field has grown tremendously too. I think, I don't know, maybe 30 years ago, if you talked about mechanobiology, you were talking more about bone strength for hip implants and things like this. There were, I think, far fewer people working in it. And I think it was more limited to bone and vascular. I think most of the people were bone and vascular. And now I think what we've come to realize is mechanics plays a role in a lot of fundamental diseases. It plays a role in aging, which is something we're all doing, whether we want to or not. And so understanding of mechanics in physiology goes well beyond just understanding, heart and blood vessel function and bone. Still two very important problems, but the field of mechanobiology has grown significantly.
So what forces do I have to apply to my body to age less?
That's an interesting question. I'm gonna hold out on that one.
Okay.
But I mean, take for instance, even something as obvious as skin, like the texture of skin and the mechanical properties of skin and the rate at which skin heals with age is all related in part to the extracellular matrix, the tissue, and the mechanical properties of that. So it's hard to ignore mechanics now. I think even the really most fundamental cell molecular biologists have come to appreciate mechanics as a really important property that we need to understand and control for medicine, but also for basic science.
So your husband is also a professor at Rice in the same department?
He is, yes.
Right? Do you guys ever argue about science, or you argue about other things?
Interesting question. We don't typically argue. It's funny, we don't actually talk science a lot. We talk science politics a lot, right? So how to navigate the academic system or mentoring practices, navigating student interactions, and
raising your scientific children.
Yeah, things exactly. Science. I mean, I think he and I have found each other a great resource because we have very complementary skills. And so there's been times where his lab has come to us and vice versa for help.
So you guys collaborate on some research projects?
From time to time. To be perfectly honest, he's 5 years senior to me. So when I was starting off, he was practically tenured when I was starting my lab. And so I got some advice that basically said, listen, you have to make sure you distinguish yourself from him because it'll be really easy for people to assume that you're the same person. So we consciously didn't collaborate for the first several years of my career so that I was very independent. And now, even now, the collaborations are pretty informal. They're more like, we need some help on a particular tool or something like this.
I mean, you guys know each other very well. There's no need to be formal.
Yeah.
But I know that you guys were also working at the same university when you were at Vanderbilt, right? How is moving as a scientific couple to a new university together, what does that job search look like? Because that sounds really like a lot of moving parts.
It is. So when we moved, collectively, we moved our entire lab. So all the graduate students, all the postdocs, and so it's about 20 people altogether. So that's complicated. I would say, moving is challenging. If anytime anyone's making a decision to move, you have to weigh the benefits versus the cost to it.
Sure.
And so there's the complications that anybody has in moving a lab. I think with the two of us, in terms of the job search, for this particular move, we weren't looking to move necessarily. So they came to us and said, hey, would you be interested? And so that's
very nice.
Yeah. So that made it a lot easier, as opposed to when I was first looking for a job. He was already a faculty member, and I was just a graduate student. And that was a little bit more complicated, right? Because
where were you guys at this point?
So we met at the
in your academic career.
Yeah.
I mean.
So we met at the University of Pennsylvania. I was a graduate student and he was a postdoc. He started his first faculty position at the University of Rochester.
Okay.
And I was a graduate student at Penn looking for a job when he was already a faculty member. And so that was a little bit more complicated because University of Rochester wasn't hiring, so I wasn't going to be able to end up there. My graduate advisor basically said, look everywhere within a one-leg flight. And I said, well, that's not ideal, but it's good advice, and so that's what we did. And I ended up with my first faculty position at Cornell, which is driving distance to Rochester. It's a couple hours, but it's doable. But it was tough. We had an infant at the time, and Cornell recruited him shortly after. And that was a really pivotal moment for us, because that was the first time that we were now together, and we weren't going to give that up. And so, but that first round was tough because he wasn't interested in moving. He was pre-tenure. You don't usually move before you have tenure. But I also didn't want to delay my start to wait for him to get promoted. And so that was probably the toughest time in our career. I think we're now in a really a really special part of our career where we have jobs, we enjoy our jobs, we really like what we're doing, and so we weren't unhappy at Vanderbilt. We weren't looking to necessarily move, but when the opportunity came along, and we saw all of the things we could do at Rice, then we got to weigh those, and it's just like any couple that are both career-minded. We have to talk about, is it good for you? Is it good for me? Is it good for both of us? And making that decision. And good for our kids. All of
them too.
Yeah.
Was it harder to move your kids or your students?
Oh, that's a good question. So for this move, actually, to Rice, the move for my kids was fantastic. So my son is currently a freshman at Rice.
That makes it a little easy.
Rice wasn't even really on his radar. He had been looking more local to Tennessee when we were at Vanderbilt. And so once he had the chance to tour Rice and get to know it, he fell in love too, and loves it there. So we love having him literally within walking distance. He does not live with us, but he can come home, and we try and leave him alone. So it was great. And then my younger son, he's in middle school, and loves his new school. It was a good transition point, 5th to 6th grade. Harder to move kids that are in high school, but I think they have both landed in better spots because of the move. I think for them, there's been huge benefit. I think they would say that too. The students were a little bit tougher sell. As you guys know, when you decide on a school, you decide on it for a variety of reasons. You typically are deciding because you like the advisor, and you like the program, and you like the city and the geography. And so, each one of my students had a lot of things to weigh in making a decision on coming and going and things like this. We really tried to take a personalized approach to each student to figure out what was going to be the best situation for them in navigating the move. And I think they're settling in now. We actually moved. You guys can appreciate this here in New Orleans. We moved during a hurricane.
Oh, beautiful!
It was the same week Beryl hit, so that made life a little tough for everybody.
A nice welcome for everyone.
Yeah. Well, welcome to Houston.
Really set your expectations there.
But they're settling in now, and I think Rice is a fantastic place. Strong medical center, strong colleagues. So. One thing, regardless of moving or not moving or wherever you are, really taking advantage of the strengths of wherever you are and really trying to benefit from that network as a graduate student is, it's not just about your research, but it's also about using the facilities that are available and the colleagues that are available and things like this. And I think they're starting to see all of the strengths that Rice offers and the opportunity to basically have networks in 2 places now, right? The benefit of having built a network at Vanderbilt and now having the opportunity to build a second network at Rice.
Have your research objectives kind of, changed even slightly as now you have access to these new resources at Rice?
Oh, for sure. And I think we'll see that, if you ask me that question again in 2 years, I think you'll see a really different outcome. And I think that's true for everybody. When I was at Cornell, the medical centers across the state. And so collaborations with the medical center were tough, but the engineering is phenomenal. The engineers on the Cornell campus are terrific. And so I think my program looked a little bit more engineering. And then when I moved to Vanderbilt with a really strong medical center, it was impossible to avoid thinking about really clinically motivated problems. And so at Rice, I think there's sort of a combination of those two things. A really strong, it's directly adjacent to the Texas Medical Center, which is the biggest medical center in the world, right adjacent to MD Anderson and Baylor and Methodist. And so I think we're going to be heavily influenced by that. And then it also has strong engineering. So yeah, to be honest, I'm sort of looking forward to seeing where my research program goes now because of the new environment.
Well, they say everything's bigger in Texas, so.
This is probably true.
So what's your approach to mentorship? I know you've mentored dozens, if not 100 students at this point?
Between master's and undergrad and graduate students, yeah. I mean, I think the important thing, I think, for mentorship is to realize that every person has different goals and different needs and responds to different incentives, right? Like what gets you out of bed in the morning, right? Like what are the things that you get excited by? And I think that's one of the challenges to mentorship, and one of the opportunities is figuring out what motivates a person and what are the things driving them to want to do good research. And to realize, one of the things about academia is that it is a stepping stone for everybody except for faculty, right? Like we're here and we're doing our jobs, and presumably we're still going to be doing that job in 10 years. But for students, it's transient, right? Like you're here to train and then to move on, and really figuring out what are the best aspects of getting students trained so that they can do what they want to do next while simultaneously doing really great science and pushing research forward. So, I mean, I think the secret to good mentorship is to realize that everybody is an individual and people are going to have different needs, and figuring out what those are.
And as, I guess, you have these students moving through this process, and then at some point graduating out of the lab, you always see that lack of, or like a drop in the skill level, right? As you lose people with these talents that they've built over this time. I guess as a lab, how do you adjust for that and, account for that in a better way?
Yeah, I mean, it's very bittersweet. I think most faculty will tell you that you get to know your faculty advisor really well. It's like a 4 to 6 year relationship. We're in it together. We're in the thick of it. And I'm always so proud of my students when they defend. I mean, it is the best day of any part of my career, or the days when students are defending, more so than awards and things like this. I mean, it's just so much pride. But it is very.
You celebrate that with a cake, right? Like a defense cake.
We do. I don't know how I got this started, but yes, every time one of my students defends, I bake a cake that is somehow shaped like their PhD thesis.
Wow.
So like a spheroid or cancer cells migrating out, or a traction force microscopy map of cell forces. Yes, it's become quite a thing. But it's really wonderful to see students be successful. But you're right, it's hard to let them go too, because it's the nature of the business. It's a horrible business model, right? Like in a business model, you want to train students, and then right as they get really good at what they're doing, you let them go. But it's really wonderful to hear from alums from the lab on what they're doing now, and all the successes they're having. But you're right, it's hard. When they leave, we work really hard in the months leading up to them leaving, working on transitioning out technology and knowledge so that the students incoming aren't reinventing the wheel. That's just sort of part of the process, and making sure lab notebooks are well kept and things like that. But yeah, it is a very bittersweet moment, defenses.
I'm just imagining like a baking show based around science. That'll be our next production.
Yeah, it's fun. I also, for my children, I bake them birthday cakes in the shape of something, whatever they're into in a particular year. And my favorite ever was my husband is a Notre Dame alum. Both my boys live and breathe Notre Dame football. I made a cake in the shape of the Notre Dame Stadium.
Wow.
It was the equivalent of like 4 cake recipes built into a stadium. So it was quite a feat. But it was so large that I normally just put it on a piece of cardboard, but it took a really large piece of cardboard. And it was so heavy that I finished decorating it, and his friends were all out at the birthday party, and I went to pick it up and move it, and the cardboard buckled.
No.
And the cake went to the ground, and my brother was visiting, and he said, it's okay, and started scooping it up and mushing it back together. And the kids didn't even notice, it was fine, but it was a cake fail for sure.
Yeah, try not to publish that one.
Yeah, exactly.
Yeah, you're probably the only scientist I know that can publish a textbook with cake recipes in the appendix.
It works. Yeah, I think the students get a kick out of it too. I don't tell them what it will be until the reveal, and I don't take requests because there are things I know I can't make. So it's usually just a surprise as to what shape the cake is in.
Mm-hmm. Is that the main way that you and your husband differ in mentorship? Does he bake cakes for his?
He does not. Although I found, sometimes the students are a little jealous and they'll order a cake and try and do something with it, but it's not even close. He and I have very different mentorship styles. That's for sure. To be perfectly honest, I think part of that comes out of him being a man and me being a woman. Mm-hmm. I think that there are different mentorship styles that come out of it. But yeah, we do find inspiration in each other and how to work with students and how to help the students be successful.
What were some things that you applied in your approach to mentorship that you saw in your mentors?
Oh, so I had some fabulous mentors. I have fabulous mentors, and I think I owe a lot to my mentors. When I was an undergrad, I started working in a lab with a graduate student who ended up becoming a faculty member. And a lot of the graduate students I was around ended up being faculty members. And my undergraduate advisor was just amazingly supportive, and even still today. So I worked with Doug Laufenberger, who really helped define the field of biological engineering, bioengineering, and biomedical engineering. Wrote a textbook, helped define the curriculum, just had a really big impact. But I think his biggest impact wasn't necessarily that. It was all of the students he's mentored and really encouraged. And I think anybody who's ever worked for him will say that he's just an incredibly supportive person. And that's where I got bit by the bug. As an undergrad, I decided I wanted to be a faculty member, and I never wavered after that. Mm-hmm. And it was largely due to that experience. And then as a graduate student, I worked with Dan Hammer, who actually was one of Doug Laufenberger's first students. So I sort of stayed in the same academic tree. Mm-hmm. And again, had a really terrific experience. Dan is, and he'll say this too, is a really hands-off mentor, but in a way that allows you a lot of freedom, right, to figure out what you want to do. And I don't think I would be as successful as a faculty member if I hadn't had the independence and freedom that he allows his students to have. And so just a really fantastic group of people. And my postdoc mentor as well, Brad Burke, really successful at putting people in academic positions. And the common denominator for all of those people is they're just really supportive. If I email any of them for help, they're happy to do it. And I hope that's what I've conveyed to my own students, which is you don't have to go in academia for sure, but knowing that regardless of what path you choose, like if I can help you, that even after you've graduated, this is what I'm here for.
So what are some careers that students that aspire to do the same kind of research that you do that can go into apart from just academics?
Oh, that's a great question. My students have done all sorts of things. All sorts of things. So one of my first students went off and worked for Merck, basically doing vaccine production, which turned out to be a really good thing.
Thanks for training him. We needed that guy.
So, I think, the skills that he learned in my lab were really the cell culture skills and really understanding how to cultivate cells and things other than just petri dishes, and how to think critically. I honestly think the most important part of a PhD is not that you learn how to use a compression tester or that you learn flow cytometry. I mean, all of those things I think we could teach anybody. I think the most important things you learn as a PhD student are how to think about a problem and then design experiments to solve it, and then applying those skills to all sorts of problems. So he went to bioreactors. I have another student who worked and went into gene therapy, and is now a CTO of a gene therapy company. Another student who graduated and works for a cancer therapeutics company up in Boston. A student who worked in Becton Dickinson, and much more instrumentation. We don't actually do instrumentation, but I think she just got hired for the problem-solving skills and the management skills. I have another student who went to law school after getting a PhD.
Really?
And now she's a patent lawyer.
Oh, okay, that makes
Yeah.
sense.
And is doing really well. So I've had students going in all sorts of things. A student who works for Stryker and does orthopedic work. So we've sent them in all sorts of directions, and I think they're hired, again, not because they understand how cells move in complex environments, which is what my lab does, but because they're good at thinking about problems critically, and pulling together resources to answer those problems.
Yeah, you talked a lot about problems and solutions. Going back to your research, your history of research that you've done, what's a problem that ended up having a really unique solution that you encountered throughout your career?
Oh, that's an interesting. I think I could point to a lot. A lot of the work that my lab does is pretty fundamental. So I could espouse on this for a while, the importance of basic science, right? I think a lot of biomedical engineering has started to get very translational, which is also good. We want to get products to shelves. But a lot of those products exist because of the basic science we learned. We learned how a system worked, and then we figured out how to manipulate it.
Right.
And so my lab's really at that level, really trying to understand how systems work. And so one of the projects that took us the longest amount of time to publish ever started off as a project just trying to understand heterogeneity in cell movement. So if you watch a bunch of cells move around in a petri dish, even if they all come from the same line, you'll find cells that move really fast and cells that move really slow. And so we just wanted to know, well, how does that translate into behavior in vivo? So if you put them in vivo, the assumption would be a cell that's really good at moving is probably going to be really good at metastasizing, spreading to secondary sites as a cancer. So we just wanted to show that. So we sorted cells based on how well they move. We put them into mice, and the exact opposite happened. The cells that were really good at moving did not metastasize. They didn't form tumors. And the cells that were really bad at migrating formed tons of secondary tumors. And so this was a real head scratcher for us. So much so when the student showed me the results, I was like, you must have mislabeled the mice. like this is an expensive experiment, but you need to go redo it because we must have mislabeled something. And she redid it, and it was the same result.
Wow.
And so that was a project where every time she ran an experiment, it was the opposite of what we would have predicted.
Those are always real tough.
Really frustrating, but I mean, I was really proud of her because she stuck with it, and we ended up getting a really interesting paper out of it and making some interesting discoveries about why that is and what's actually driving metastasis and spread of cancer. And so, that was just a great example of where we got the unexpected results, and the unexpected result turned out to be the interesting result.
And what was your experience trying to publish this work? Because I'm sure it wouldn't have been easy.
Well, we knew it wasn't going to be easy, and so that's why it took so long to publish, because we held on to it for a really long time so that we could make sure that we understood it from front to end before it went out, as opposed to just saying, look at this surprising result. We really wanted to understand why it was that way, and so that's why it took so long.
Did you guys ever race the cancer cells like racehorses? Take bets, anything like that? What was the betting pool for the cancer cells?
Unfortunately, they're not quite that interesting to watch in that way. A couple microns a minute is the best you can get them. So it's a slow, not quite Kentucky Derby level.
Right. So I know you did some work on science policy as an expert advisor to the federal government on biomanufacturing. Tell us about that experience.
Yeah, this actually sort of came about just sort of accidentally. So they invited me to the White House to this forum to hear about the Biden administration opening up a huge amount of support for biomanufacturing. And so I think they were just trying to get thought leaders into the room to talk about what this is going to look like, and really not even just to talk about it, but also I think to advertise it so that we could go back to things like BMES and say, look, this is coming down the pipeline. Let's get prepared. Let's think about how we're going to capitalize on funding mechanisms and how we're going to be training students, things like this. And so that was what I really felt my role was not so much to guide the government as much as to take what the government was doing and bring it back into the biomedical community and say, okay, so how are we going to respond to this, and how are we actually going to use it to start training students? And the field of biomanufacturing is super exciting. And biomanufacturing, it's producing vaccines and antibodies, but it's also biofuels and bioweapons and things like this. And so all of the cybersecurity that goes into it, and the financial planning for it, and building up the manufacturing sites. And so on the U.S. scale, it's really exciting because it's going to take some of the communities where the manufacturing has gone overseas, and those communities have really suffered financially for it, and bringing a new type of cutting-edge manufacturing to those communities, and figuring out how to train people to work in that manufacturing setting is really exciting. And so I think part of what we need to do as educators is think about, well, how are we training students to work in the biomanufacturing landscape? I mean, there's the basic science and the products you're going to make, but also how do you scale those up and how do you actually manufacture them? So, I think I felt like my role in that context was really trying to educate our community on what the federal government was doing, so that we could figure out how to mobilize appropriately. I was involved on the other end too. There was an initiative a number of years ago assessing the role of physical sciences in oncology research. And so the NIH and the NSF really wanted to understand, what are people doing globally in this? What are people in Europe doing? What are people in Asia doing? And so they sent a team of us to visit a number of sites around Europe and Asia. It was probably the most intense travel experience I've ever had. We were at 1 to 2 different sites per day for a week straight, and we did that twice. So we hop, skipped, and jumped around Asia, and then did it again, hop, skipping, jumping around Europe, basically interviewing scientists, visiting universities, and talking about what they were doing in that space, and ended up issuing a report saying, this is what people are doing, with some guidance on how is the U.S. going to keep up or lead in this area. And that ended up resulting in a large investment of the NIH into the physical science oncology program, really growing the number of engineers and physicists and mathematicians working in cancer research. And that was, like 15 years ago or so. So if you look...
Different presidential term.
Yeah. But if you look over the last 15 years, we'll take BMES as an example. 15 years ago, there wasn't a session on cancer and engineering. And now there's probably about 500 or 600 submissions a year of people working in that space. So it's grown absolutely substantially, of people with really strong engineering skill sets who weren't thinking about cancer now are, and making strides and trying to understand how cancers grow and how we can treat them and how we can prevent them in a community that otherwise wasn't really thinking too much about cancer.
How was it meeting the president as a president yourself? Did you feel very diplomatic?
Well, unfortunately, the president wasn't there. It was a number of his high-ranking officials making the announcement, and it was...
You were the president.
I mean, honestly, it was exciting to be in the room because there were a lot of groups and Congress people basically coming together in a bipartisan way to talk about the importance of biomanufacturing to the U.S. And everybody was on the same board, right? Like nobody was, there wasn't a debate. I mean, I think everyone in the room was in agreement that this is something the U.S. needs to invest in. It is the future, and I mean, that is exciting.
And as I guess when you were making these visits to other labs across different countries, I guess how was your experience with going and learning what these groups were doing? Did you see any pushback from the countries itself, or was it more like an open invite for for you to come?
Yeah, that's a really astute question, because it was definitely a mix. There were some people who were just really excited that the U.S. was interested in learning about them, and then people excited to talk about their research and to collaborate and to figure out what else we could do better. But there were certainly groups who said, like, this feels a little bit weird. Like, why are we going to share our science with you? My philosophy on that is cancer is a tough problem that we're suffering worldwide from, and it's not a competition. I think we can all agree we just want it cured. And so I think working together to whatever extent we can should be the goal. But you're absolutely right. There were some people who were a little bit suspicious. We weren't there to spy on them. We were there to get the vibe of what the culture in this area was, to try and inspire where we should head next. And I think that report was made public, so it's you can download it whoever you are, whether you're here or in France or wherever you are. And so, and that was the goal, right? That anybody could use that report to justify or inspire or to help direct where research should go.
Hopefully good vibes in science. That's what we're going for.
Yeah. Collaboration works.
Right. So yeah, coming kind of back to your research again, I know we talked briefly about cellular migration in cancer. I guess, do you see any avenues through which where we can actually explore therapeutics for cancer through like assessing this migration studies that you've done?
Yeah, that's a great question, and I think it's a huge area for opportunity. So if you look at the different classes of chemotherapeutics that are available, the biggest market is just trying to stop cells from proliferating, right? Most of the microtubule inhibitors, the taxanes, and taxols are all really just trying to prevent cells from proliferating. And then more recently, there's a class of immunotherapeutics, right? Trying to get our own immune system to kick in and go after cancer cells, which have been very successful for certain classes of cancer. There's been attempts to target angiogenesis, the ingrowth of blood vessels, as a way to starve tumors. Those have met with mixed results depending on cancers. Migration, though, which is pretty fundamental to the spread of cancer. So what you'll hear if you hear toxin cancer, the statistics people show is basically if a person has a primary tumor and it hasn't spread, their survival rate is incredibly good, right? If you can find it early and it hasn't gone anywhere else, it can be removed or it can be treated using radiation or chemotherapeutics, and the patient's survival rate is 90+% for most cancers. Not all, but most cancers. If a cancer has spread, even as something as simple as skin cancer, which you can see, if it goes too long and it spreads, the survival rates go into the single digits. And so the idea of targeting migration to me seems huge, right? Because that's where it becomes dangerous. If the cancer never gets out of the primary tumor, then typically you're going to be able to treat it. But it's that step of migration and dissemination that is particularly potent. And so I think there's a lot of promise there in terms of targeting migration, survival in the bloodstream, homing to secondary sites. That is something that to date has not been targeted. So I think there's a lot of opportunity there. The challenges with that are the same as you'd imagine with anything, which is there's a lot of, you want to make sure you're going after the cancer cells specifically, right? You don't want to target every cell. And how do you figure out what those differences are that allow you to go after the cancer cells?
So in terms of therapeutic approaches, what's the pros and cons of developing a new drug or repurposing a drug that was maybe used for a different application that finds use in your particular setting?
I think that's a good question. In terms of repurposing drugs, I think there's some opportunity for that, but for the most part, I think we've to some extent exhausted it. I think finding new therapeutic targets is when I look at research and I look at what has been making it through the FDA pipelines and shown the most clinical efficacy, it's not, at this point in cancer, to me, it doesn't feel like it's repurposing. It's people looking at completely new avenues. So immunotherapies are a great example. The rate at which new immunotherapy targets are coming out is so promising, right? That there's a lot of potential there. The other place that my lab has recently gone, which I think a number of people are thinking about, are metabolic effects. So, we talked a little bit about one of the struggles within drugs in general is making sure they're hitting just your target and they're not hitting other cells and other off targets. And metabolism is an interesting one because there's a lot of metabolic pathways that cancer cells use that healthy cells do not. So it opens up a potential therapeutic avenue that we hadn't been looking at before. And again, if you look at FDA approvals, there have been a number of metabolic inhibitors that have come out that have been moving through the clinical trial pipelines pretty successfully, more so than at a higher rate than many other drugs have. So my own feeling is that there's a lot of opportunity to look, now that we have better sequencing technologies and better ways to profile cells and to look at the secretome and to look at metabolomics and really find pathways that are unique to particular cancers or unique to particular individuals and look at new ways of going at them.
Awesome. Well, before we get going, is there any last minute advice you want to give to the people out there watching?
I think maybe I'll take it full circle. I think service to your community can be as important as the science that you do. And I think, service comes in a lot of forms. So, service in professional societies. Right now, there is some distrust of scientists in the public view. I think as scientists, one of the best things we can do are make sure people understand what we're doing and how we're doing it. We're not hiding the cure for cancer. We're working on it every day. And a lot of that comes with, good science communication. And I think that is something all of us have to get better at, is communicating what we're doing, not just to each other, but to the broader world of the importance of research. You'd find there's some really educated people who don't understand the value of NIH funding and what the importance of NIH funding is to curing cancer, preventing COVID and creating vaccines, curing heart disease. The NIH is at the core of that. And we can't expect people to understand the importance of tax dollars to the NIH if we're not talking about how funding is utilized and the importance of it. So I think, that comes as a service, right? Like most people aren't winning awards for science communication for the most part. It's hard to publish your scientific paper on science communication, but I think things like this are a really good service and helping to communicate what scientists are doing so that the public can understand what the science process looks like and the importance of putting tax dollars to that. So I think if I had advice, my advice would be don't underestimate the value of science communication, disseminating your work, being able to communicate your work to a broad audience, and devoting some amount to that service to help promote your own field, because even the best science is only good if it's communicated. You could do something fabulous, but if you can't communicate it, it just doesn't matter.
Well, we really appreciate you coming to communicate with us. It was an absolute pleasure. Yeah. Thank you.
Thank you, guys.
Thank you, Dr. Reinhardt.
All right, y'all. That's a wrap. That was awesome.
Yeah.
Great job.
Good job with you guys.
Wow, great time. Were you waiting?
Yeah.
I was like, whoa, you came in 3 seconds earlier.
You would have ruined the whole thing. We'd have to start again.
Cut.
Oh, no, that was terrific.
Yeah, I think we had like pretty good take.